Next presenter is Reiji Nakashima. He received DBE from the Nagaoka University of Technology in 2020. He is now in master course of Department of Electronics and Information Engineering in the Nagaoka University of Technology.
Thank you for the introduction. I'm Reiji Nakashima from Nagaoka University of Technology. My presentation for today is entitled 360-degree see-through full-parallax light field display using a holographic optical element. And this is the outline of my presentation, and I'd like to begin with the introduction. In recent years, various displays have been developed and constructed. Among them, especially spherical or cylindrical display is effective for digital signage. These displays have wide viewing zone that enables observers to see the image while walking around the display, and multiple observers can view it at the same time. Also, 3D display is an effective way for advertising because 3D image attract people's attention strongly. Additionally, see-through display is likely to be used as a digital signage recently. This is another effective way to attract people's attention. A display that has these characteristics is expected to bring high effectiveness as a digital signage. Next, I will explain about the related works. These are the cylindrical 3D displays. The observers can walk around these displays and see the 3D image without any specific glasses. These displays realize horizontal parallax. However, when the observers move vertically, the image becomes incorrect. This means the displays do not realize vertical parallax. This is a 360-degree transparent holographic screen display. This display uses holographic optical elements, in short, HOE. Due to the characteristics of volume holographic optical elements, this display can realize see-through. But the displayed image is 2D. The 2D image is projected on the cylindrical screen, and the image is synchronized by tracking an observer. So, only one observer can see the correct image. Based on these related works, we propose a 3D display with the characteristics as shown below. First, wide viewing zone. The 3D image can be observed 360 degrees around, and the observers can walk around the display. Second, observable by multiple viewers. Multiple observers can view the image at the same time without any specific glasses. Third, see-through. Observers can see the image, which appears to be floating in real scene, and it attracts people's attention. Fourth, full parallax, realizing vertical and horizontal parallax. I'd like to move on to the proposed method. When we see a real object, we sense 3D by the parallax, which means that we can see different sight depending on the position of our eyes. Light field method is one of the ways to realize the parallax. The display reproduces the rays of light emitted from real objects. Then we can see different images depending on the position of our eyes, like we see the real object. It is 3D images. The proposed display realizes light field. Next, I will explain about the whole display system. The proposed display consists of a high-speed projector, a hyperboloid mirror, and a rotating HOE screen. The rays from the projector are reflected by the hyperboloid mirror, and the rays are incident on the rotating HOE screen. And then the rays are diffracted by the HOE screen, and the direction of the rays are changed. As the HOE screen rotates, the rays are scanned horizontally and vertically. Also, since the projection image is refreshed accordingly, full parallax light field is realized, and the observer can see the 3D image. The proposed display consists of the projection system and the cylindrical HOE screen. I will explain about the projection system first. In normal projection, a projector projects image on a flat surface like this figure. In the proposed display, the projection system projects on the cylindrical surface like this. So a hyperboloid mirror is set on the top, and the rays from the projector are reflected by the mirror. Then the image is projected onto the cylindrical surface. Next, I will explain how to scan the projection rays horizontally. This is the cylindrical surface from top view. For example, if a square lens is set on the cylindrical surface, and as the lens moves on the surface, the direction of the ray from the projector, as shown like this red arrow, is changed, like this. The ray from the projector is scanned horizontally by the moving lens. And while the ray is scanned horizontally, the projection image is refreshed fast enough that our eyes cannot detect it. Then we perceive the rays with different color depending on the horizontal angle of rays at the same time, like this figure. Therefore, horizontal parallax is realized. Next, I will explain how to realize the vertical parallax. If multiple square lenses with different height are set on the cylindrical surface, like this, same principle of horizontal scan is applied on each lens that I've explained in previous slide. And as the cylindrical surface rotates, the vertical component of the direction of the ray is constant through one lens, but it is changed when the lens is shifted to the next lens. If a parallel ray is incident on the lens, like this, the ray is focused on the focal point as shown as the black dot, this. Since the cylindrical surface rotates, the ray is incident on the second lens. This is first lens, and this is second lens, and this is third lens. And hits first lens and next, as rotates the cylindrical surface, hit the second lens, like this. And third lens. Therefore, the ray is scanned vertically among these lenses. Since the projected image is refreshed during scanning the ray with different color that depends on the vertical angle of the rays are emitted, as shown in this figure, like this. Then vertical parallax is also achieved. Horizontal and vertical scan are realized like this figure. This is horizontal and this is vertical scan. Then the rays with different color that depends on the vertical and the horizontal angle of rays are emitted from the cylindrical surface like this. However, if multiple lenses are set on the cylindrical surface, it causes some problem. First, see-through cannot be achieved because the rays from background are also affected by the lenses. Second, the vertical scan by the lenses, as I've explained in previous slide, is only applied under the condition that the rays from the projector are parallel. But the actual rays from the projector diverge from a certain point, as shown in this figure. So the function that should be achieved is not the same as normal lens. To solve the problems, HOEs are used for the scan instead of the lenses. Holographic optical element, or HOE, is an optical element that is made using the method to make hologram. Holographic optical elements have optical function by the diffraction. And if it is volume hologram, HOEs have angular and wavelength selectivity, which means that the HOE affects only rays with specific wavelength or angle. By recording the HOEs with the same shape of waves as the rays from the projector, the HOEs in the proposed display scan the rays from the projector, same as the principle in the previous slides. Also using the selectivity, the rays from the projector are affected by the HOEs, but the rays from background are not affected and just pass through the HOEs as shown in this figure. This blue arrow is the rays from background, and the red arrow is from the projector. Therefore, the HOEs realize the function to scan the rays from the projector and also realize see-through. By aligning the HOEs on cylindrical surface like this, the cylindrical HOE screen is created. And by combining the screen and the projection system, which consists of a high-speed projector and a hyperboloid mirror, the proposed display is realized with these characteristics: full parallax, see-through, and wide viewing zone. Next, I will explain the design of the display. The projection system consists of the high-speed projector and the hyperboloid mirror. This causes a problem. Because of the characteristics of the projection system, the pixel pitch differs depending on its height on the cylindrical surface. The mirror shape affects the distribution of the pixel pitch significantly. Therefore, the parameters of the mirror shape were calculated so that the difference of the pixel pitch can be reduced to the least possible extent. The mirror shape is defined by hyperboloid function. The formula is shown here, this formula. Y is vertical direction, R is radial direction. A and B are the parameters to be calculated. Display conditions are shown in this table. Here, as the result, when A is 94.3 and B is 77.8, the difference of the pixel pitch is reduced. The mirror shape is shown here. This blue line is the hyperboloid mirror, and this red line is the rays from the projector. The ray from the projector incident on the hyperboloid mirror and reflected by the mirror and incident on this HOA screen. Next, I will explain the simulation. We conducted computer simulation to make sure the 3D image can be observed properly, considering the pixel pitch using ray tracing method. The condition of simulation is shown here. For this simulation, pinhole model projector is used so that the effect of the aperture of the projector is not considered. Also, the diffraction efficiency of the HO is not taken into account. The simulation was performed with 5 viewpoints in total. The center viewpoint is at 500 mm away from the display with a height of 100 mm. This is equivalent to the half of the cylinder's height. Also, 4 viewpoints at 60 mm up, down, left, and right from the center viewpoint are defined. This left figure are the ideal image from each viewpoint, and the right is the simulation result. In this result, we can see the parallax is appropriate parallax is achieved. Focusing on the right side of the cube, in the ideal image, you can see this side is changed according to the eye position, camera position, and you can see the same things happen in the simulation result here and here and here. So we can say the horizontal parallax is achieved properly. And also focusing on the top side of the cube here and here and here. In the ideal image, you can see the image is changed according to the camera position appropriately, and the same things is happen in the simulation result. You can see, and I can say the vertical parallax is also achieved. However, when you look at the result closely, especially the top side of this cube, you can see the jagged pattern, and this happens because of lack of number of the horizontal direction. In other words, the angular resolution is low. And I will talk about the conclusion and the future works. In conclusion, we proposed 360-degree see-through parallax light field display using holographic optical elements. And we designed the display. Also, we simulated and made sure the proper parallax is achieved. As the future works, we will improve the jagged pattern that we saw in the simulation result. Then we will create actual HOEs and develop the prototype. With this, I'd like to end my presentation. Thank you for your attention.